Hello, chemistry students. This is Professor Sean McMahon with Chapter 5, Nuclear Chemistry. So I did skip this chapter. Typically, I skip this chapter and save it for the end, just because it actually works a little bit better, because we'll see with the nuclear chemistry, unlike our normal reactions where atoms don't really change, we'll see with nuclear chemistry, when we balance these, you'll actually see elements changing their composition. So I typically say this, it's a good review for us to talk about isotopic notation, which is something we've seen earlier when we talked about atomic structure. You'll also see, typically because of time constraints, I do omit some portions in the lecture of Chapter 5. For example, I omit the topics of fusion and fission. I omit the topics of using nuclear energy as a power source. I omit some of the discussions with Geiger counters and how to count rads and things like that, the disintegrations per minute. My focus for this is typically going to be basically two concepts, which are the different types of radiation and nuclear reactions and how to balance them, and the half-life calculations. So I just want to let you know that the topics that I'll be covering is not all of it. And again, this is geared towards more of an introductory level, but I hope you like this last discussion. So here we go, nuclear chemistry. So radioactivity is a term that really can have a negative connotation. So I want to cover this topic and make it as simple to understand as possible. Essentially what it is it's the emission of an energetic particle out of an unstable nucleus. So you have a nucleus that is kind of unstable and it shoots out a particle to help stabilize it. So you can think of it as shooting out something that's kind of volatile. So the way that we show these radioisotopes, okay, because we'll see when we look at the periodic table, they're not going to always match the average atomic mass that you see on the periodic table. The atomic number, the number of protons, will be consistent with the elemental symbol. So we've talked about that. To make the element what it is, you look at the atomic number. But we'll see with these radionuclides, the mass number is very different from the average atomic mass many times. We'll also, you may recall, we could use subatomic particles like a proton symbol, if you ever see that. A proton, the atomic number is 1, the mass is 1. For a neutron, it doesn't have, it's not considered an atomic number because that's the number of protons, but it does have a mass. And then the electron symbol, because there's a negative charge, you typically put a -1 charge, but it has relatively a negligible mass, so you'll see a 0 for the mass number. Now, some books will show these symbols for the decays. I tend not to when I do the nuclear reactions, but I just want to show these symbols because in some cases you'll see something similar. So what are the types of radiation? Nuclei are unstable, typically when they're too large, and that means they don't have a good ratio of neutrons to protons, because typically that's what is the mass of the entire atom. It's in the dense nucleus, and the nucleus contains the neutrons and protons. So when there's not this kind of sweet spot, and typically for smaller elements, there's 1 neutron to every proton to be stable. As the elements get bigger, that ratio slightly deviates to where there's about a 1.5 ratio of neutrons to every proton. And what happens is, if you don't have this kind of sweet spot of balanced nuclei, they start shooting out things from the nucleus to lower either the total mass or the atomic number or the mass number in the nucleus. And what they're shooting out are essentially different types of radiation. And that could be an alpha particle, a beta particle. Typically, alpha and beta decay is coupled with gamma rays. That actually doesn't have mass, but we'll talk about it. Or a positron, which is essentially very similar to a beta It's just similar to a beta decay. It just has, instead of shooting out a negative particle, a positive particle. So this is kind of the sweet spot we see in yellow. We see that it's not always a perfect one-to-one ratio. And we see with the lighter elements like carbon, we see that one-to-one ratio because we see that the mass number is 12. Well, mass number is the number of neutrons plus the number of protons, and the atomic number is 6, that's the number of protons. So 6 plus 6, we have the mass over the neutron over the proton number equal to 1. Then as elements start getting heavier, as we see in mercury, we start noticing, all right, I have 80 protons. 80 minus 200 means there's 120 neutrons. 80 divided by 120 gives me that sweet spot of 1.5, which makes this heavier element more stable. Okay, so that's kind of the sweet spot. We see it's kind of skewed from a perfect one-to-one ratio. So what are the different types of radiation? Well, Rutherford discovered that there's 3 types. There's the alpha radiation, alpha rays, alpha decay, and then there's the beta rays, beta decay, and then there's the gamma. And what we notice is that the alpha particle is very similar to essentially a helium nuclei. It's 2 protons and 2 neutrons, and they would have a 2+ charge. So you can think of it as, this is very common with very massive radioisotopes. You have this huge nucleus and it's unstable. So the best way to stabilize it is to shoot out 2 neutrons and 2 protons to make it smaller and to decrease that ratio of neutrons to protons, okay? By doing that, you actually change the atomic number, and now you have a completely different element. With the beta, it essentially is, you can think of it as you're shooting out an electron, okay? That's essentially what a beta particle is, because you're converting a neutron into a proton, and as a result, you shoot out a negative particle. The gamma radiation is essentially just electromagnetic radiation, and it doesn't have a charge or a mass. So when we look at these plates, we see towards the negative charge plates, the alpha decay approaches because it has a 2+ charge. And the positive plate, we see the beta because it has a -1 charge like an electron. And the gamma just goes straight through because it has no charge, no mass. So let's focus on the types of radiation and how to identify it. So in an alpha radiation, that occurs when you have an unstable nucleus shooting out an alpha particle, okay? So what is an alpha particle? 2 protons, 2 neutrons. So we're trying to show in this example where this unstable nucleus is shooting out 2 neutrons, 2 protons to make it smaller and get closer to that sweet ratio of 1.5 or 1. So in nuclear equations, right, we're showing essentially what it's breaking down. So in an alpha decay, we're going to omit the 2+ because we're only kind of looking at what's left behind in the nucleus. And what we see is in the alpha decay, the reason why we write a 2,4 is, remember, there's 2 protons, and over here, there's 2 protons and 2 neutrons being shooted out. So that's why the mass number is 4. A lot of times for a decay, what they'll write for an alpha decay, instead of helium, they would actually write the alpha symbol. I'll just keep it simple and keep it as helium. But what we notice is that the original parent nuclei, in this case, uranium-238, I know it's uranium because it has 92 protons. If I look at the periodic table, the average atomic mass is not 238, but this is just to show you it is an isotope. When it has an alpha decay, you notice that the atomic number is 2 less, because remember, I lose 2 protons in an alpha decay. And the mass number is actually 4 less because I lose 2 protons and 2 neutrons from the nucleus. So we are primarily interested in the changes in the nucleus. So we don't really care about the 2+ charge to write it out to make it easier. And for the alpha particle, we just omit the 2+. So the term nuclide is used in nuclear chemistry to mean a specific radioisotope, okay, or specific isotope. The original atom is called the parent nuclide, and then the products are the daughter nuclides. And the daughter nuclides have different atomic numbers than the original parent. So when an element emits an alpha particle, the number of protons in the nucleus changes, so it's a completely different element. So in chemical reactions, and this is the difference between balancing nuclear reactions and chemical, the elements retain their identity, right? We're just using balancing by coefficients, okay, to make sure there's the same law, according to the law of conservation of mass, the same number of atoms on both sides. That's why we change only the coefficients. Here, we're balancing the atomic mass and the atomic number. So we're actually changing the identity of each element. So here's an example, right? If we look, we have uranium-238, and on both sides, the mass is 238, right? So uranium, it's just 238, but with the thorium, it's 234, but remember, I lost a mass of 4 because the alpha decay is 2 protons and 2 neutrons. If I look at the atomic number, it's 92, and thorium is 90, plus the 2 from the helium, that's 92. And now that's why I'm a different nuclide, because the atomic number went from 92, once it's shot out, this alpha decay particle and shoots it out, what's left behind is only 90 protons, because I've lost 2 protons and 2 neutrons. And now I'm a completely different element. I'm thorium. If I look on the periodic table, I would see atomic number 90 is thorium. And the mass might be different because this is a different isotope. And on the periodic table, it's an average atomic mass. So when you're balancing the nuclear equations, the best thing to do when you're trying to figure out the daughter nuclide is when you start with the parent nuclide, if you know it's an alpha decay, write out the alpha decay. So you would do the alpha decay is 2 protons, 2 protons, 2 neutrons makes the mass of 4. So how can you figure out the unknown daughter nuclide? Well, we know that the mass has to equal 232. 4 plus what number is 232? 228. We know that the atomic number has to be 90. The alpha decay has an atomic number of 2. So 2 plus what number is 90? It's 88. So the daughter nuclide is 228 for a mass number and 88 for an atomic number. So how do you figure out the elemental symbol? You go to the periodic table. You don't identify the isotope from the mass, because remember, the masses can change because isotopes have different number of neutrons. So how do we identify the elemental symbol? We look at specifically the atomic number. So when you go to the periodic table and you look at the atomic number 88, you're going to see that it's radon. And that's what you're going to write out. So this would be a balanced nuclear reaction for an alpha decay of thorium-232. The reason why I say 232, it tells me the mass, because I know thorium always has 90 as an atomic number, otherwise it wouldn't be thorium. And I see with the alpha decay, because I lose 2 protons, I change the identity to a new element. So let's try this, right? U-233. So I know it's an alpha decay. What's the easiest way to balance it? Start with the daughter nuclide of the alpha. So the alpha decay, remember, 2 protons and 2 neutrons, that totals a mass of 4. So now what I want to do is I want to look at 92, subtract 2, I look at 233, subtract 4, and what's left over? I'm going to get a 90 and a 229. And when I look on a periodic table, I see for 90, that's thorium. And now I look at radon 222, and I do the same thing. I want to first do the nuclide, the daughter nuclide I know, the alpha, which is the 2,4, subtract 2 from 88, 86, subtract 4 from 222, 218, and now I get the 218, 86 radon. Okay. And now with the americium, if I look 95, 241, I'm going to subtract 2, I'm going to get 93, and subtract 4 from 241, 237. And that's how you balance it. Now that's an alpha decay. What's important when we talk about radiation also is people hear, well, it causes problems. And why is that? Well, with radiation, it's this high-speed particle, and it has a charge a lot of the times, and it's going to hit molecules and atoms. And what it does is it essentially knocks off electrons. It basically, because if you think of an atom or a molecule, you have your nucleus, and then you have your electrons outside of the nucleus. If I have a high-speed particle that collides with the valence electrons, it might strip them and cause them to be ionized. So that creates ions, and that creates charged particles. And that's not good for living organisms, right? It could cause damage, cell death, or just it won't reproduce properly. It could cause proteins to denature. There's a multitude of problems that it may cause. So the ability of radiation to ionize molecules and atoms is called ionizing power. However, another component is, can the particle penetrate through matter? So in order for radiation to damage molecules within living cells, it has to penetrate into tissue, essentially. It has to get to the cells. So there's something referred to as penetrating power. And in some ways, they're kind of inversely proportional. So what do I mean? If I think of an alpha particle and its potential damage, you can think of it as the semi-truck of radiation. What do I mean by that? It's a really big particle, okay? It's shooting out this huge particle from the nucleus, which means it has a lot of potential to damage cells and molecules. Of all the radiation, right, the alpha particle has the most ionizing power. But because it's so large, it doesn't have a very good ability to penetrate, right? So you can think of it as this semi-truck trying to go through a traffic jam. It can't really get through it. It can't maneuver very easily through it because it's so massive. So because it doesn't penetrate very well, we can easily stop an alpha particle emitter, right? You can use a sheet of paper or clothing, okay, even air, because it'll start colliding with air particles and eventually just drop down due to gravity. So low-level alpha emitters that are kept outside of the body are relatively safe, right? Because you can use a sheet of paper, your clothing, it's not going to get in to any cells in your body and cause any type of damage, even though they have high ionizing power. The problem is if you ingest one or inhale, then it has direct access to cells, and then that could be a problem. So typically you want to avoid, ingestion or inhalation and high alpha emitters, basically. So what about beta radiation? Well, this is, again, when you have an unstable nucleus, but it shoots out a particle. So you can think of beta radiation as essentially an electron, a negative particle. And that occurs because the neutron changes to a proton. So how does it do that? How do I make something neutral change it to something positive? Well, I have to shoot out something negative. And that's essentially what your beta radiation is. It's basically an electron being shot out of the nucleus. But what happens? Even though the neutron and the proton have the same mass, so the mass number does not change, what does change is the identity of the element because now the atomic number goes up. So because neutrons and protons have the same mass, the mass number doesn't change, but the neutron becomes a proton, so now my atomic number goes up 1 because I shot out. That's why we have a -1 for beta. It shot out a -1 for the atomic number. So the symbol we're going to use is 0, -1, and E. Think of it as an electron. Some books use the beta symbol. I'm just going to use E to keep it simple, consistent with your book. So notice that for the mass number, there's a 0. Why? The relative mass of an electron or a beta decay compared to an atomic mass unit, the mass of a proton or a neutron, is negligible. It's like 1/2000. So we're not going to include that. But again, realize that the atomic number is going to change, right? Because of that -1. We're going to add a +1 to the atomic number of the new daughter nuclide because the neutron's converting to a proton. So the mass doesn't change, but the atomic number goes up 1. So here's an example, right? I have radon, and it emits a beta decay. So what does that mean? The easiest way to write it is first write out the beta. So the mass does not change because a neutron converts to a proton, but I'm going to increase the number of protons. So I'm adding 1. That's why this is a -1, because 89 minus 1 gives me the original 88. So we'll also see that the 228 is the same on both sides. So again, with the nuclear equations, I always tell students to focus on, when you're writing out the daughter nuclides, there's going to be an unknown. Start with the known and then perform the calculation. So if we wanted to do a beta decay for each of these nuclides, we would start the 40 for potassium is the mass number. Where do I get the atomic number? Again, I look for the elemental symbol of K for potassium and I see it's 19. So I know I'm telling you it's a beta decay. So I'm going to write 0 minus 1. Okay. So -1 plus what number is going to give me a 19? 20. 20 minus 1 is 19. The mass number doesn't change. It's still 40. How do I figure out the elemental symbol? I look on the periodic table and I look for atomic number 20 and I see it's calcium. So I could do this for the helium-6 isotope. Okay. Remember, these are unstable isotopes. That's why they're decaying. Because if we look at the periodic table, the average atomic mass for helium is roughly 4. Why? Well, that's because those are the stable nuclides or stable isotopes. So they tend to go to the stable isotopes. Those are more abundant. The isotope helium-6 is unstable. It actually decays and changes. That's why it doesn't contribute to the mass that much, okay? Because normally in nature, you don't see it because it decays too fast. So what do we notice? First going to write a beta decay. So -1 plus what number gives me a 2? Well, wouldn't that be 3? So the mass doesn't change because, again, the neutron, I get 1 less neutron, but I add a proton, right? So it's lithium because I look on the periodic table, the atomic number is 3. I could ignore the mass number because with isotopes, the masses are going to be different than the average atomic mass. But when I look on the periodic table and I see a 3 for the atomic number, I see that it's lithium. And I could do the same for the sodium-24. Subtract 1 from what number gives me 11? 12. So this would be magnesium. And I know that because I look for the atomic number 12 and I see that it's magnesium. So with beta particle potential damage, instead of the Mack truck, right, the semi, this is more like a mid-sized car. And it's less massive, so it has less ionizing power. However, because it is smaller, it can penetrate a little bit better. So instead of just air or a piece of paper or clothing, you actually need like a sheet of metal, like a sheet of aluminum foil or some wood to stop it from penetrating. So low-level beta emitters outside the body pose a higher risk than an alpha emitter. Inside the body, they have a lower risk. Why? They're not that Mack truck just slamming into things and ionizing them. They're less of an ionizing power. So they have more of a penetrating potential, but less ionizing power. So you might remember I said there's a positron emission, which is essentially the same as it's like a beta emitter in terms of mass, but instead of a negative charge, it has a positive charge. It's not a proton though, okay? It doesn't have that mass. So that's why we're still gonna keep the symbol as an E, right? Because it has a similar mass to an electron, and that's why you see here for the mass, it's 0. But it's positively charged. That's why it's +1. So why is it positively charged? Well, the proton becomes a neutron. So how does something that has the same mass, because protons and neutrons have the same mass, how does it get rid of its positive charge? Just shoot it out. So it just shoots out this positron, which has a similar mass to electron, which really is nothing compared to the protons and the neutrons. But now what's going to happen is I'm going to see that the atomic number is actually going to decrease, even though the mass number is the same. So for positron, we're going to use this symbol. The O in the upper left of this radioisotope means that the mass number is 0. And the +1 in the lower left reflects that the charge of the positron, and it means that the atomic number is +1 in the nuclear equation, which means I'm going to see a decrease in the nucleus of the original radioisotope, and I'm going to have one less proton. So here's an example. So if I have phosphorus 30, which has an atomic number of 15, and I shoot out a positron, I'm going to write 0 + 1. So what number +1 gives me 15? 14, right? So why did this happen? I still have the same mass because one of the protons converted to a neutron. So I lost the positive charge and it became a 14. Okay, but I still have the same mass because the neutron has the same mass as the proton. So the nuclear equation is balanced. The sums of the mass numbers on both sides are the same with the atomic numbers. The positron emission, right, is similar to the beta as far as ionizing power and penetration power. So it has less ionizing power than an alpha, but it has more penetration ability because it's smaller. Let's try to write out some nuclear equations with positron emissions. So here I have carbon 11, and I always start with the daughter nuclide that I know, which is, in this case, the positron, okay? And I see that this is +1. So +1 plus what number is going to give me 6? 5. So this is boron. So I go to silicon 26. How do I know that the atomic number is 14? I look on the periodic table. I see that the atomic number for silicon is 14. Just like for carbon, the atomic number is 6. Why is it silicon 26 as a radioisotope? Well, that's because it's the mass number, and that's how we can identify it. The mass is different because isotopes have different number of neutrons. So now, if I shoot out a positron, 1 plus what number is 14? 13. I look on the periodic table, the atomic number 13 is aluminum. The mass stays the same because the proton just converted to a neutron. So I have one less proton. I have one more proton, but the mass is still the same. Manganese 50. Remember, start with the positron. 1 plus one number is 25. 24, chromium. Same mass number. Gamma radiation is different from the alpha, the beta, and really when I say beta, I'm including the positron because it's a similar size, just different charge. But with gamma radiation, there is actually no matter. It's just electromagnetic radiation, right? So it has an extremely short wavelength, but it has no charge. It has no mass. It's typically coupled with another type of radiation. So if I have an alpha decay, I might also shoot out a gamma particle. And when I say particle, really what I mean is electromagnetic radiation, a form of light. We learned this when we talked about light. So this gamma ray doesn't have mass or charge. So here's an example, and we actually did this when I first introduced the nuclear equations, and I introduced the concept of alpha decay, where I took uranium-238, and I know uranium has an atomic number of 92. I said it was an alpha decay. So 92 minus 2 gave me 90. 238 minus 4 gave me 234, the thorium 90. But what I didn't write is this also can emit some gamma radiation, which is light. Now gamma, right, it has low ionizing power, but high penetration. You can think of it as a motorbike of radioactivity, right? They have the lowest ionizing power, but high penetration. So stopping a gamma ray is really difficult. In fact, how does energy travel, right, in space through these long distances from electromagnetic radiation? And what's the electromagnetic radiation that travels the furthest? Gamma rays, right, all the way from the sun and other solar systems, right? We measure gamma ray. We also measure radio waves and things like that, but the gamma rays, because they have, you know, they're really short frequencies, they can travel long distances, okay? But how do you stop gamma rays? Well, you need some really dense material like lead or concrete. So when we summarize the ionizing power and penetration power of the different nuclear decays, we look at the alpha particle, which is the biggest particle, has the most ionizing power because when it collides, it knocks off electrons very easily, but it has low penetration power. And that's because it's so big, I can just take a piece of paper and block it. Okay, it won't get inside my body. So you can see here, here's the alpha particle. The clothing is protecting this person. Now the beta particles, they're smaller, right? And it's basically when the neutron changes to the proton, so I'm just shooting out like this negative charge. So it's much smaller. So it still has a little bit of an ionizing power, but what it really has is a better penetration. So that's why for a beta particle, I need something like an aluminum sheet, right? Or a really thick lab coat and gloves to protect me, not just regular clothing. Positrons, similar to the beta emission, it's the same thing. So they're, you know, usually for a positron emission, when they show the beta, they just put a little plus sign because it's positive instead of negative. That's the only difference. But the other one is you got the gamma ray. And the gamma ray has very low ionizing power, but you know, it's so small, it can go right through you. So your summary is essentially, you know, in all of these decays, you have to first figure out what type of decay. Is it alpha? Is it beta? Is it positron? Then you got to look at the parent nuclide. Oh, sorry about that. You got to look at the parent nuclide. And then using the type of decay, determine one of the daughter nuclides. And from one daughter nuclide, deduce the other. And then for ionizing power, it's based on the sizes. Okay. So, and as a really quick review, we see, you know, with beta decay, what do? I'm shooting out essentially a helium, 4, 2, subtract 2, 4. With beta decay, I'm shooting out an electron. So we have a -1, no mass change. So you have 2, 2, 8. How am I shooting out a negative? I'm increasing the positive charge, the number of protons. So -1 plus 89 gives me the original 88. And for the positron, I'm shooting out a positive particle. So what am I doing? I'm essentially decreasing the number of protons. Why? Because a proton becomes a neutron and shoots out a positive particle. Right? So these are kind of just the opposites. Here I have a neutron change into a proton, so I increase atomic number. Here I have a proton changing to a neutron, so I decrease atomic number. Right? Neutron changing to something positive, I got to shoot out a negative. Something positive changed into something neutral, I got to shoot out something positive. So that is our synopsis of nuclear equations and balancing them. What are the different types of decays? How to write the radioisotope symbols. So this is nice to review for our isotopic symbols and finding on the periodic table the element's identity based on atomic number, and taking into account that the mass number is the number of protons and the neutrons. And that's why we can have so many different isotopes. Stable isotopes, when they're lighter elements, they tend to have a 1-to-1 ratio between neutrons and protons. As the elements get heavier and heavier, that ratio is kind of skewed, where you have a 1.5 number of neutrons to protons as a sweet spot. If you don't, as a result, they become unstable and you have these decays, whether they be alpha, beta, or positron, and we can balance these equations, and then we can also discuss based on their size, their ionizing power, and their penetrating power as well. So I hope you enjoyed this lecture, and on our last lecture for chapter 5, we will discuss how we can determine how long something's been around through something referred to as half-life decay. You may have heard this with carbon dating, and that will be our next topic. So thanks for watching, and I'll see you next time.